Go.
Hello everyone. Today I'm going to present a paper entitled Estimating Training Data Influence by Tracing Gradient Descent. This paper was presented at ULIP's conference in 2020, so it's a bit earlier paper, but it's still relevant because the area this paper actually focused on is quite new and did not advance very well. So I chose this paper because this paper seemed to me interesting because I have been working on explainability tools for a bit longer, for several years. But mostly I focused on post-hoc interpretability and feature importance things. But this paper is a bit different in that perspective, that it actually proposes an idea of explaining a test sample on the basis of the influence of the training samples. Okay, so this paper was written by actually a few authors from Google in 2020, as I said. So explainability can be applied in different settings, but mostly people have applied explainability in supervised settings. So in supervised settings, there can be two kinds of explainability. One is called feature importance, where we actually focus on how a particular prediction, how a model focuses on specific features to make a particular prediction on a test sample. That is what we know as feature importance. Another kind of explanation in supervised setting is called example importance, where we don't try to focus on the features of that particular test sample. Instead, we try to find some training instances that better represent that what are the basis of the model it used to make this prediction, how the model has learned during the training process to make this particular prediction, that kind of things. In another kind of setting, people have tried to use explainability, that is in unsupervised setting. So that is actually out of the scope for today's discussion. So I will not focus on this slide any longer because we have already described what is post-hoc explainability. That means given an input and model, and the model generates the prediction, and then we use some explainability tool or explanation method to identify some relevant features that the model used to make this prediction. That is traditionally called feature importance. But the paper we are going to discuss today is not about feature importance that I have mentioned earlier slide. This paper is all about example importance. That means showing some training samples that actually give us some sense why this model made this prediction, or what are the basis that the model used to make this prediction. So the algorithm this paper actually proposed is called tracing. In other words, we can name it tracing the influence from the training samples. That means it computes the influence of a training example on a prediction. And it does it for all of the training samples. If we don't mention that how many training samples we want, it usually does it for all of the training samples and orders all of the influences by their rank. And
sorry, by the rank in meaning what?
By their influence score. Okay. Rank means influence score. So the main idea is, for example, we are showing here an example. For example, we are on the left, we are given a test sample, and it shows 3 proponents and 3 opponents. The 3 proponents means, I will explain proponents and opponents a bit later. So the main idea of calculating influence is how does the loss on the test point change during the training process. That is the main idea of this tracing algorithm. And proponents are those training samples that actually helped the model to reduce the loss. And opponents are those training samples that actually encourage the model to increase the loss for this test sample. That means opposite. Proponents help the model to reduce the loss for this test sample, and opponents actually encourage the model to increase the loss for this test sample. That means conflicting examples.
Is it like the positive and the negative samples that you have in the field of contrastive?
No, it is not related to contrastive learning anyway. So let me explain it in another way. For example, 3 and 8. So if we consider 2 digits from MNIST, 3 and 8, so 3 and 8 have some similarity, right? So 8 may confuse the model to learn 3. So 8 might be working as an opponent. That means
So is this like you take the data set, remove that specific sample, retrain without it, and you see that the loss goes down?
yeah,
That means this is an opponent. If you put it back, the loss goes up.
yes, that is one of the goals of this algorithm. That is, it is actually not intended solely to work on generating explanations. Rather, how we can correct the model, how we can better train the model by identifying some, for example, some opponents, as you say.
Well, I'm trying to mechanically in my head define those opponents and proponents, or by how would I do it? And the one way to do it is just removing them. It's like leave one out. Train on everything, and then compute the loss on your sample, the reference sample. And then remove each of them one by one, retrain the model and compute the loss, and then you can rerun.
Yeah, so yeah, I understand.
Kind of like,
I understand.
I don't know how they do it, but
yeah, but this paper actually was not interested in retraining. Totally, they were not interested in retraining.
yeah, this is too much computation, but mechanically, this is what they want to know, right?
Yes.
Somehow more efficient.
Yeah.
Okay. Yeah. Thank you.
And the goal is actually not only to generate the explanations for the test sample, rather how we can correct the model for its better training. For example, which samples are disturbing, which samples are confusing this model. So let's remove those samples and retrain it for our ultimate production, for example. Okay, so this paper actually uses the idea of fundamental theorem of calculus, but using fundamental theorem of calculus while doing the deep learning training, it is not possible. So they actually adopted first order gradient approximation to make an approximation to first fundamental theorem of calculus. We'll see. And they used multiple, yes.
What is this theorem?
Yeah, we'll discuss fundamental theorem of calculus in a bit. Yeah. And they have actually saved multiple checkpoints during the training process and then cherry picked some layers of deep neural network. So why did they cherry pick? Because considering all of the parameters of the model might be very large. So considering all of the parameters will incur huge computations for this influence score computation. That's why sometimes they suggested to use few layers instead of using all of the layers just for the computation purpose. So what is fundamental theorem of calculus? Fundamental theorem of calculus basically decomposes the difference between a function at 2 points. And this decomposition can be approximated using the gradients along that point. And we'll see in a minute how we can do that. For example, this one. Consider this one as your gradient of the loss function. here A represents loss function. Assume that A represents the loss function. And if the function we are showing here is the gradient of the loss function. So the fundamental theorem of calculus is saying that if we want to calculate the difference between two functional values at 2 points, we can do that by calculating the integration of the gradient between these 2 points. That is what we can see. But for the deep learning training, if you consider deep learning training, we have only access to the gradients. At specific points, we don't have the continuous access to the gradients. So we can only make an approximation to this. So they use this first order approximation to calculate this integral, to approximate the difference of the two functional values at 2 consecutive points. So what are 2 consecutive points here? Because we are dealing here with model parameters. So each time we update the weights, we actually reach a new point, right? So the difference between earlier parameter set and the new parameter set is called the distance here. Okay, so ideally, what will be the influence? They have, because they are calculating influence for each training sample. And ideally, we would assume that the model was trained based on stochastic gradient descent. That means only one sample in each training pass. And if we consider all of the update step, a particular training sample was used, and if we can sum up all of the loss reduction, then we can directly compute the influence of that particular training sample on a test sample. Here, G is the training sample, and G prime is the test sample. So if you have any question at this point, does it make sense, the equation?
Yes.
Yeah. Okay. So, so initially, so what will be the total influence actually? Suppose the initial parameter vector space. Okay. So initially, we assume that the parameter set was W0. And finally, after the model training, the parameter set is WG. That is trained set of parameters. And suppose the model has used n number of training samples. So what will be the total influence or total loss reduction for the test sample Z prime is equal to the loss based on initial parameter and minus loss based on the final parameter. Okay. So based on first order gradient approximation, we can write the loss equation as the first line. As we can see that L WT plus 1 Z prime is functional value at 1 point, and L WT Z prime is functional value at another point, as we have seen here. So, okay, so A here represents L. Okay, so this difference can be approximated by the gradient times the increment, as we have seen here. The gradient, as I have mentioned earlier, that F here is the gradient function, and that means the gradient of the loss, we can assume it. So it can be the difference of the original functional values at these 2 points can be approximated by the product of the gradient times the increment. So similarly, we can see here that the difference of the two functional values, for example here, can be approximated by the gradient of the first point times the increment. So we can write from the update rule of the stochastic gradient descent, we know that the difference between these weight parameters will be equal to the learning rate minus learning rate times the gradient of the loss with respect to the model parameters. So if we simplify the top equation using the middle equation, then we get the third equation. So this is the equation this paper actually used to calculate the influence. So influence score of the training sample Z on the test sample Z prime can be calculated now using this formula. It means that consider only those training steps where this training sample G was used and approximate using the formulation we had discussed earlier. Any question here? Because this is the main equation actually.
What is the last part of the first equation for norm two ways?
It is the Taylor series. We're just saying our errors will be quadratic in this. Yeah.
For example,
small number, if the difference is small number squared even smaller, so we can ignore that.
It's like
magnitude of the error of this representation.
Can you see the excess?
Yes.
So that part is actually being ignored. So yeah. So that is the VO of. Okay. So, but this is actually not feasible because generally we don't train a deep learning model based on stochastic gradient descent. At least we use mini-based stochastic gradient descent. So we have to get a formulation for mini-based stochastic gradient descent at least. So they have proposed this formulation for calculating influence of a training sample based on mini-batch. That means though all of the training samples are used at a particular training step, so that's why they used the gradient of that particular step and distributed all of the gradients by the size of the batch. B is the size of the batch here, and then assigned those contribution to each of the training samples. But it is still not feasible because they actually considered every training step in the earlier formulation, for example. This one. That means consider all of the training step where this particular sample was used. For example, a model might be trained in 1,000 epochs, right? So it is not possible, and the model might be very large, and it could have billions of parameters. So it is not feasible to store all of the parameters in advance. So that's why they have used a heuristic formulation of this influence function. That's called influence based on checkpoints. So they used few checkpoints, usually regular after some epochs, and then they use those checkpoints to calculate the influence of each training sample. So though this paper actually uses all of the formulation based on stochastic gradient descent, but they say that it is also possible to derive similar formulation for other experimental setup. For example, Adam optimizer or any other optimizer. They said that derivation is possible, and they did not show any proof, but they assume that if we use checkpoint version of this formulation, then it would be quite similar, regardless of the optimizers we are using. And they have also mentioned that, for example, if this influence calculation or formulation could also be used for hypothetical influence calculation. For example, say we have an example that was not used during the training process, but we want to calculate hypothetically that how much it would influence the training process if it was used during the training, even though it has not been used. So it is also possible to hypothetically calculate the influence of the sample that was not used in the training process. Okay. So the evaluation approach, it is interesting because there was actually no consensus evaluation approach to evaluate an approach that is calculating influence of training samples. So they used self-influence score. Multiple papers who have actually worked in this area of calculating influences of training samples have used this metric to evaluate their respective approaches. So self-influence score means calculating influence of the sample on itself. That means instead of using a test sample, it calculates the influence of a training point on its own loss. That means here Z and Z prime are identical. So the idea here is, as this was mainly used to identify mislabeled examples. So the intuition here is, if a sample was mislabeled, that means it's an outlier. So outlier sample has a general tendency to push the model more than a natural sample, than a correctly labeled sample. So if a mislabeled sample pushes the model stronger than a correctly labeled sample, that means the self-influence score will be larger.
Can you explain that again? Like incorrectly labeled samples, how will they be a strong proponents for themselves? Won't they be? I mean, if it's an outlier or if it's a complete, like the example that you mentioned, 3 and 8.
I think it is more like intuitive. For example, if you are natural, for example, if you try to be who you are, you don't have to force. But if you, I am trying to explain philosophically.
Yeah. But there's an easier explanation, right? If I see 1,000 apples that look like apples, and then I pick up one banana and I'm like, this is an apple. You have to do more work, like cognitively. To like say, oh, that thing is not shaped like an apple.
For example, 3 is not 8, right? So if a sample is originally 3, but it has been mislabeled as 8. So if the sample wants to convince the model I'm 8, it had to push the model stronger. That's the intuition they used.
The gradient will be higher on that sample.
Assuming the features are vastly different, right, for that sample,
So that's why they use the self-influence score. So self-influence score, they calculated self-influence score and used in the setting of identifying mislabeled samples. We'll see in a minute that how they used this experimental setting to evaluate their approach. Okay, so the first experiment was conducted on Cypher 10 dataset, and they used ResNet 56 model to train it. And first they train a model based on current data, and then they corrupted the data set with 10% modifications of the label. That means 10% of the samples are mislabeled, for example. And then they train the model again. And so the accuracy drops from 93.4% to 87%.
Where was this published?
This paper.
Yeah.
This paper was published.
Was it? That's hilarious to me.
Yeah.
Because this is the only data set they did.
No.
Yeah. Okay.
They used multiple data sets. This is the first experiment.
Okay.
And they actually, with the final model, that means with the mislabeled model, with the incorrect model, they actually tried to identify the mislabeled example using the self-influence score. So the idea is the fraction of mislabeled data recovered for different prefixes of the rank order. We'll see in a minute in a plot that will make more sense. For example, here, let's focus on the right-hand side figure. That will be more interesting and will make more quick sense. So, for example, the x-axis here shows the fraction of training data checked, and first of all, we need to keep in mind that they actually calculated self-influence score of all the training samples, and based on these self-influence scores, they actually sorted in decreasing order. That means the highest first and so on. So as the idea is the mislabeled samples have the highest scores. So in that rank order, mostly the mislabeled samples will appear first. So they are showing here, for example, with 20% training data check, they are showing here that more than 80% mislabeled samples have been identified with their approach. But in other baselines, for example, influence function or represented method, the number of mislabeled samples identified is around 30%. But, it's around 45% or 50%, or with 20% training data set, training samples checked. The other baselines only could identify 50% mislabeled samples, and they could identify more than 80%. Any question here? Because this is the main result they are showing in evaluation. Does it make sense? Or
it's very interesting that they were able to recover like more than 80% of mistake.
yes, just with 20% training data checks, based on their ranking, they have seen that with first 20% of their ranking, they already got 80% of this level sample.
But does the checkpointing make any difference in this? Like, the third point is like considering both weighted and equally weighted checkpoints. Does that in any of these parts, does the weighted checkpoints make more difference, or the equally weighted checkpoint? Like which part of checkpointing will be much better?
Yeah. So in this evaluation, as we can see that it didn't make any noticeable difference, right? Because the upper two plots are actually trust in CP and trust in CP equally weighted. So normally trust in CP uses the weighted pattern. That means it uses the learning rate of that particular checkpoint as the weight of that checkpoint. But in equally weighted means all of the checkpoints are treated equally. And on the left side, it is showing that with the identified mislabeled samples, if when they would correct those mislabeled samples, then the accuracy would improve faster, right? . And in this plot, because they are showing that not all of the checkpoints actually focus on similar training samples, rather different checkpoints actually focus on different training samples, different classes. So they are here they are showing that at different checkpoints they are actually trying to, based on different checkpoints, they are trying to identify mislabeled examples from different classes. And now they are showing that different checkpoints are actually able to identify mislabeled samples from different classes, right? So for example, the 30th checkpoint, we see that the mislabeled samples from the DR class are identified mostly, right? But for the 150th checkpoint, the mislabeled samples from the truck class are identified mostly. On the top, middle here. That's what they trying to show. That means during the training process, not all of the checkpoints or not all of the epochs actually focus on all of the samples equally. Okay, so this is similar experiment they conducted on MNIST. They used MNIST to make it more simpler, and they tried to use trace in instead of trace in CP. They actually tried to estimate the difference between trace in CP and trace in. Trace in means all of the training steps were considered. Trace in, and trace in CP means only the checkpoints were considered. So the similar results we are seeing here. That means with only 20% of the training data checked.
You don't like everything? Sorry.
I'm just, you know, I'm bitter and I'm tired, so I'm not gonna say anything.
Okay, so we are seeing similar trend here. That means with only 20% training data checked, they have been able to identify approximately 95% or more than 95% mislabeled samples.
Do you have any error bars?
Yeah.
This is actually a very interesting work practically for us here, maybe even
It's
for.
the last part of my dissertation. We can use this method as another evaluation.
Actually, yeah, but for fixing the mislabeled data, like somebody has done this work here, but also maybe by harmonizing the databases and stuff.
So this is very important and interesting in the, so there was a recent challenge that Google introduced in Google as well. It's called the machine unlearning, where they want to identify which sample is not important and which can be like, which is going to make your accuracy or whatever lower. So if you can use this for that approach as well, I think that would be very interesting. Because you're basically checking like which samples are not important. You can identify which samples are not important, it's create something interesting.
Yeah, but which samples are conflicting, which samples are mislabeled. There are actually several applications.
I mean,
and I asked ChatGPT, what are the advantages of using tracing or this influence function? So ChatGPT actually provided a broad list.
Because this paper is in the data set. It's 2020, right?
Yeah. No, it's not quite similar to what this paper said. I have checked the description of the ChatGPT and I read this paper. So this is not same. ChatGPT used its own knowledge. Yeah.
it's kind of a local influence method, though. Like, that's sort of what I was thinking. So, you know, when you're just computing the gradients, right, you're only going to be looking at local changes in the loss. I think there's room to innovate on this if you can look at it. I mean, even when you were mentioning like removing samples, and yeah, that's, you know, removing individual samples might increase performance slightly. There's a much more complex picture in terms of global learning behavior, interactions between groups of samples and stuff. So there's a lot of stuff to do to improve on this method.
Okay.
Second order stuff is the first step, yeah.
So this is a friend of influence functions, which are the Hessian. They're essentially this, but with the second order statistics, the thing that they don't do is they don't integrate, right? They don't sum over the checkpoints, which I think is actually kind of novel and may resolve some of the critiques of influence functions. I don't know, but
They used influence function as baseline.
What's strange is I couldn't find any critiques of this. I didn't look very hard, but there's always a critique of explainability methods. If you have an explainability method, in 4 months, there will be a critique of it. I couldn't find.
One criticism is their formulation is approximation. For example, the batch formulation. This formulation is this formulation is quite approximation. We cannot guarantee that this is the influence of the training sample. They are using the influence of the batch and distributing it equally to all of the training samples. So this is an obvious. This is an obvious form.
But it integrates over batches, and that's we do that all the time.
Yeah, but they are calculating influence for each training sample, but using the information batch-wise and distributing to each training sample.
Do they use large batch sizes?
Yeah, but aren't you like marginalizing over batches by doing that summation over batches? No, the batches doesn't matter. You're doing it for each batch. No.
No, it is the checkpoints are based on each batch, right?
But the batches change.
Yeah, the batches effectively change, etc. If you more do that long enough, you kind of the effect of the batch will be washed over. Hopefully.
Hopefully, yeah. Okay. So here we are trying to actually show that the effects of checkpoints. That means, do we need to consider all of the checkpoints, or do we need to consider which checkpoint? Initially, as we have also faced during explanation estimation, that means initially the model goes from the very chance level to, for example, 60% or 70%. So initially, the model hesitates a lot. And this paper says that we should not consider all those checkpoints. That means the initial checkpoints should not be considered. And they are showing here, okay, so they are showing the relationship of trace in CP versus approximation tracing. So approximation tracing actually uses all of the checkpoints. And they are showing here the correlation between considering only a particular checkpoint versus considering all of the checkpoints. So, for example, as we can see from the first box plot, that middle checkpoint is more correlated than the last checkpoint, because the during the last checkpoint, actually the model has very little to learn, right? But during the middle checkpoint, it is still learning. And then they use the 3 evenly spaced checkpoints that is more correlated to the tracing. So I should mention that tracing, approximate tracing means considering all of the checkpoints. As the study used multiple checkpoints, the correlation actually increased, as you can see here. And they have used another formulation to save computation that is called random projection. So instead of calculating all of the gradients, they have used random projection during training time and saved some of the random projections of the weight space so that we can use them during computation to save this intensive computation space. So, but if you use random projection, you have to compromise with the performance a bit. So here they are showing some examples of proponents and opponents from MNIST data set. For example, the test sample is 3, the first one, the upper one. The test sample is 3, it has been identified as 3, and it is showing some proponents. So tracing CP and representer, these two methods actually represent consistent proponents. But for example, the influence function proponents are actually not very consistent. For example, 9 has been the proponent of 3 for the first example, as you can see. 9, 5, so 9 and 3.
I kind of disagree philosophically with
Which one?
but for one, I think this classification of opponent is problematic. Again, talking about this long-term influence of samples and interactions between samples. And I think this idea that they're saying, well, a sample from that class has to be helpful for that class. Like that, I think that's not true, right? So a model could see a 5 and it could be helpful for learning what a 3 looks like.
Yeah. That is what we are seeing here. For example, tracing. See here, for 3, the proponents has been 8. It is very close to 8, the fourth one on top in proponent group. It is very.
I would agree only, you showed us the plot for mid checkpoints and the end checkpoints and the initial checkpoints. I would agree if this is only for the initial checkpoint, because that time the model is just learning. So they don't really know what features are correlated to that.
No, they are using trust in. See, they are using trust in, not trust in.
No, I'm not talking about trace. I'm just talking about consider just a normal machine learning algorithm. 3 convolution layers. What happens there? Even if you put MNS data set, even if it's 5 or 3, your model is basically learning the samples and the features from 5, 3, 8, but they still classify it correctly if you give them a 3 or 5 or 8. In this case, what I'm not able to understand is what are the cases where they might fail to identify those features, because of which the gradients will be higher, obviously, because you're learning it. But in the end, what are you actually trying to do with that? Do you get my question? You know that you're learning from the model anyway. But in this case, what is that specific thing that is because of which you want this tracing?
I think the model actually subgroups samples. I think, for example, initially, to learn what is 3, it actually does not rely only on 3. I think it also uses samples like 8, samples like 5. That means it probably subgroups first and then refines later, maybe. Otherwise, 9 would not appear as proponent, right?
Yeah, that makes sense.
So these are actually other samples from Cypher 10 dataset. Lots of proponents and opponents, so I don't have anything to say here. But the one thing I should mention that they actually did not rely only on Cypher 10 and MDS dataset as maybe Brad was thinking, that they trained their model on Cypher 10 and MDS and published in UDIS. They also showed several applications. That means They trained a text model, a computer vision model on ImageNet, and maybe a regression model. So they showed several applications.
Still better, because we did all that as well. They said it still wasn't enough.
Yeah. So this is the conclusion slide. So this method is very simple because you don't need to know lots of theories of linear algebra or deep learning or machine learning. You just need to have some basic ideas of gradient descent, checkpoints, loss functions, and so on. And though this paper actually uses stochastic gradient descent, but they think, intuitively think that this method is general and it could also be applied for other optimizers and any architectures in any domain. And the method is versatile in the sense that it can explain, as we were talking about, that it could be applied to identify mislabeled sample. It could be applied to explain a single prediction and many other stuff, right? So that's all. If you have any questions at this point.
I have a complaint. So I liked how much work they did on checkpoints and like what checkpoints mean, blah blah blah. Sergey, cover your ears. One of the big issues with interpretability and explainability is size of a model, the number of parameters, the depth, the width. Bean Kim's work a few months ago showed this. And they had an opportunity here. I don't know, maybe they did later, I don't know, but to test like, oh, what layers are actually the most influential? What layers should we be targeting? What layers are actually just kind of adding noise? But instead, it looks like they're just like, oh, let's do the last layer. Let's say the last layer.
This could be one of the criticisms of this paper. Yeah. For example, in many experiments, they did not use all of the parameters because it is very computationally intensive. They just chose, for example, last one.
Yeah. Which
so they are calculating all of the influences only based on last layer parameters.
To their defense, just to oppose Noah. Last layer is what everyone does anyways, right? Like when we're fine tuning, when we're blah blah blah. So it's kind of they went with the ChatGPT way. Do what's the masses are doing, just as last layer.
That's how you get accepted in neurons.
Well,
And that's the viewers are the masses, and they just think in templates, patterns, and yeah, the last layer
you
makes
should
sense.
just always do what everybody else does.
Yeah, it's called regression to the mean.
I think we could use this as for the last part of the dissertation that I did, where we were looking at the auto differentiation, to look at the gradient structure and during training. I think we can use this as a straw man and a basis to
maybe implement it slightly more engineering way, like spend time on implementation, so it is constant factor slower.
Yeah, and we can use like low rank approximations of the gradient rather than the full thing, and there's a lot we can potentially do with the AD perspective on it.
Let me make a recommendation. Influence functions, I think, are a lot more common and popular. So you might, if you're going to look at this as like a baseline, and since they do second order.
So
just as like an appendage to the method that we already have, I think, is what I would do.
So the main difference, I actually did not include this slide due to shortage of time.
I mean, it's the aggregation.
Yes. So the main difference between influence function and tracing. So how they are treating these tasks. So influence function actually tries to understand what happens to the loss if we drop at any point and retrain a model.
Ideally, but influence functions as repurposed for neural networks are just the Hessian of the
I know, but they are calculating Hessian, but the main goal they are trying to achieve is, let's drop a training sample. What would happen to the loss of a test sample if we retrain? So that is the goal they were trying to achieve, but they did not retrain it. I understand they were using Hessian. But here they are not trying to solve that hypothetical scenario. Instead, they are trying to
estimate how much loss decreased from the starting of the training till the end of the training for this test sample.
And that aggregation that they do, I think, is maybe the most valid part of their method.
Yeah.
But I don't know, I think influence functions are more ubiquitous. They're more common. Not that means anything.
Yeah.
I just think it's interesting.
I think it does mean something. I think the fact that they're looking at first order statistics is a big shortcoming of the method.
Probably.
Yeah.
And Hessian computation is heavy, right?
It's huge. It's a
It is
big
huge.
problem. If you want to do an influence function on it.
Maybe that is one of the main selling points of this paper.
Yep.
That is Hessian computation is used.
Is there a follow-up work that they did on this paper? Is there any follow-up work?
For this work, no, but I know another work of this line, but they did not actually use the gradients. They actually used some model agnostic approach to do the same thing of what this paper is doing, but not based on gradients. That one is called data model.
So, but philosophically speaking, that's interesting, like what the levels of interpretability. This is kind of like interpretability by example. It's the craftsmanship, sort of not explaining the theories of why it works, but just look what I'm doing, I've done it last time, it worked. And that's why you do it, and as a society, we develop from that level of interpretability to kind of theories, concepts, and more abstract notions.
So if you're Plato. No, if you're Plato, you start with theory, abstracts, and concepts, and then everything flows from that.
No, I think our learning curve had a collapse there. We collapsed to Plato,
I see.
and then we collapsed and started over. The whole ancient Greek civilization just collapsed. Well, the Romans, they collapsed. Yeah, I think the approach to interpretability that way, and it's all on the record, of course, but I still think in medicine we're using that old approach because biology is so complicated that we just go by example. Okay, we diagnose you with this because this and this and this person. It's like we don't have a clue how their brain work, but they had the same.
They're two separate questions. I mean, it's interpretability, but they're two separate questions. They're essentially asking like, what subject, what sample is kind of either maybe out of distribution or too far outside of their own zone, whatever. The other question is about feature space. And they're separate questions. And they need to, I don't think they're
not really about feature space. It's like,
that's what I'm saying. The other methods, post hoc methods, saliency, IG, blah, blah, blah.
Yeah, I don't understand. I don't like. Yeah, they're kind of weird. In the sense of, okay, they're showing here, but what does that mean? But when you're saying, okay, you are like that, that's why you're in class, like kind of like 10 years neighbor in a sense, but 10 years neighbor in this embedding space of a black box model. It's like with it, this model found you similar, and this model is very good. That means like not really. This model predicts you to be that because it also predicts those other things to be that, and we really followed through those cases. Like in medicine case studies, it was right, and so you must be this. That's
what I meant by the positive and the negative features.
There's no features, no features. It's very different than no sense. Like it's just like splitting this thing into features, we can only do if we have a theory of how this works. But in biology, we don't have a complete theory, right? So, and so it's kind of like, oh, yeah.
We have a theory. We don't use it at all, and we just
it's like it's not that each theory supposedly works at its own level of complexity, and we have a lower level how neurons work, and we don't know how the brain works. It's sort of like that, so it's easier.
We have a lot of good ideas. We can map the brain at a high level pretty well.
I don't know how the brain works.
You don't know how the brain works at all? I feel like you've said the opposite. That is not true. You told me once that we perfectly understand how memory works. I want that on record. I want that on record. You said that.
Not anymore. You should have recorded back then. I've changed my mind since then 50 times. Thank you everyone for joining. Thank you Mahfuz for presenting.
good job.
Yeah, thanks. We can definitely use this for that work in January, some way.